We got into this whole subject of systems of linear equations right after I'd introduced the notion of invertibility of a matrix and said that it was hard to determine when a particular square matrix was invertible. You'll remember that the definition of invertible was that a square matrix A was invertible if and only if there existed a matrix B such that AB and BA were equal to the appropriately sized identity matrix. In this video, we're going to make this connection between invertibility and row-reduced echelon form. Specifically, what we will do is prove that a square matrix A is invertible if and only if you can get from A to the identity by doing a sequence of row operations. This is quite a complicated result, and we need a few lemmas on our way to proving it. So here's the first one. What it says is that if X is an m by m matrix in row-reduced echelon form, so a square matrix in row-reduced echelon form, then either X is the identity matrix or X contains a column with no leading entry. Let's think why this is true. So what we will do is assume that every column has a leading entry, and we'll deduce that actually X has to be the identity matrix. Now if every column of X has a leading entry, well then you have m leading entries. And the leading entries each have to be in a different row. You can't have more than one leading entry per row because the leading entry is the leftmost element in a non-zero element in a row. So if every column has a leading entry, then there's got to be m leading entries, and so every row has a leading entry too. We're going to introduce some notation now. Ni is going to be the number of the column in which the leading entry in row I appears. So for example, if your matrix looked like this, 0, 1, 0, 0, and then a bunch of other stuff, then N1 means the number of the column of the leading entry in row 1, and you can see that the leading entry in row 1 appeared in column 2. So in this case, N1 will be equal to 2. That's the meaning of these Ni's. Now, the row-reduced echelon form condition tells us that the leading entry in row 2 must be to the right of the leading entry in row 1. And the leading entry in row 3 must be to the right of the leading entry in row 2, and so on. So in terms of column numbers, what that means is N1 must be strictly less than N2, and N2 must be strictly less than N3, and so on up to Nm. But the numbers N1 up to Nm are the numbers 1 up to m in some order. And the only way to arrange the numbers 1 up to m in increasing order is for that order to be 1 is less than 2, is less than 3, is less than 4, up to m. So what it must be happening is that n1 must be equal to 1, and n2 must be equal to 2, and n3 must be equal to 3. So in fact, the leading entry in row 1 must be in column 1, and the matrix must look like that. And the leading entry in row 2 must be in column 2, and so on. We must look like this. But because columns with leading entries in a row-reduced echelon form matrix have zeros everywhere else, we've got to have zeros like this. Okay, it now follows that your matrix is the identity matrix. So we're done. Here's another lemma that we need. What the lemma says is that if E is an invertible matrix and A is a square matrix, and they both have the same size, then E times A is invertible if and only if A is invertible. One direction of this proof follows from something which we mentioned quite a few videos ago now. A product of invertible matrices is invertible again. That was in the video where we introduced the notion of invertibility. So if A is invertible and E is invertible, then EA is also invertible, which gives one direction of our lemma. For the other direction, we're going to assume that EA is invertible, and we now have to prove that A is invertible. So let's suppose that EA is invertible, and we'll use the name B for its inverse. What that means is that EA times B and B times EA is equal to the identity. That's the definition of B being the inverse of E times A. Now I claim that A is invertible, and the inverse to A is B times E. And the reason for that is that we know B times EA is equal to the identity. So if we do BE times A, then by associativity I can re-bracket that as B times EA, and since B is the inverse of EA, this is the identity. Conversely, or rather to do the other equality, E times A times B is equal to the identity because B is the inverse of EA. So taking this equation and multiplying it on the left by E inverse, we get E inverse E inverse E A B equals E inverse times I, which is just E inverse, so AB is equal to E inverse, and then multiplying on the right by E, we'll get that ABE is equal to E inverse times E, which is of course equal to the identity. So A times BE is equal to the identity. Now we've shown that BE times A is the identity, and A times BE is equal to the identity, and therefore A is invertible and its inverse is B times E. We've done both directions of this lemma, so we're finished. Having done those two lemmas, we're now ready to prove our main theorem, which says that a square matrix A is invertible if and only if there exists a sequence of row operations R1, R2 up to Rn, such that when you do those row operations to A, you get the identity matrix. So just to be clear, I don't mean that this n here is the same as the size of A. This n could be anything. It's not necessarily connected to the size of A. All I'm saying is that a square matrix is invertible if and only if there exists some finite sequence of row operations which you can do to A in order to get the identity matrix. We can do the proof. So here is a proof of the if direction. This is a proof that a square matrix is invertible if there is such a sequence of row operations. So if such a sequence exists, we're going to define EI to be the elementary matrix associated to the ith row operation. So EI will be the ith row operation in our sequence applied to the identity matrix. Then you'll recall that Rn of A is equal to Rn of E of the identity times A. That was a theorem we proved a couple of videos ago, that doing a row operation was the same as left multiplying by the corresponding elementary matrix. So using that result a lot of times, I can see here I've got a k where I ought to have an n, so let's just correct that. There shouldn't be a k there at all. What there should be there is an n. So using that identity a lot of times, what we get by replacing R1 of R2 of R3 of up to Rn of A with A times En times En minus 1 and so on, we get that the product of the E's multiplied into A gives us the identity. So it's a little easier to understand what's going on there if you think about a small example. So let's suppose we were in a situation where n was equal to 2, so R1 of R2 of A was equal to the identity. Well, in that case, you know that R2 of A is equal to the corresponding elementary matrix to R2 multiplied by A. So that will be, with our notation, E2A. But then we can use this result again. So doing R1 is the same as multiplying by the elementary matrix corresponding to R1, which is E1. So from that we get E1, E2A equaled the identity. So this equation here is simply what you get by using that fact a number of times. Okay, but all of these elementary matrices are invertible. We proved a theorem saying every elementary matrix is invertible. We also know that a product of elementary matrices is invertible. So the product, which we have here, E1 up to En, is a product of invertible matrices, so it's invertible. If we give it the name E, then what we have is that E times A is the identity. So now multiplying that equation on the left by E inverse gives us that A is equal to E inverse. E was an invertible matrix, so E inverse is an invertible matrix, so A being equal to E inverse is also invertible. We've now shown that if there's a sequence of row operations which when you do them to A you get the identity, then A is invertible. Let's now do the opposite direction. So we're going to show the only if direction, which is that if A is invertible, then there's a sequence of row operations which you can do to A, ending up with the identity matrix. The way we'll prove that is by supposing that there's no sequence of row ops taking A to the identity, and we'll deduce that actually in that case A was not invertible. That's the contrapositive of the thing we're trying to prove. So what we do know is that given any matrix at all, we can do a sequence of row operations which result in a row-reduced echelon form matrix. So given that there's no sequence of row operations taking A to the identity, when we do a sequence of row operations to A to get a row-reduced echelon form matrix, the row-reduced echelon form matrix we get, which I'm going to call X, cannot be the identity matrix. It must be something else. Now the first lemma we proved said that since X is a row-reduced echelon form matrix, which is square and which is not the identity, it must have a column with no leading entry. So there's a column with no leading entry. That means that there are n-1 or fewer leading entries. But since A is n by n, well then there must be a row with no leading entry. If a row has no leading entry, it must be a zero row. So this matrix X has a row of zeros, and you know, because we proved it before, that a matrix with a row of zeros is not invertible. What we can do, though, in the same way as in the if part of this proof, is argue that there is an invertible matrix E such that E times A is equal to X. E is the product of the elementary matrices corresponding to the row operations which took A into row-reduced echelon form. Just like on the previous slide, E times A is equal to the row-reduced echelon form of A, which in our case is this matrix X. But X isn't invertible, and our second lemma then tells us straight away that since E times A is not invertible, but E was invertible, it must be that A is not invertible. And that completes our proof that a matrix is invertible if and only if there is a sequence of row operations which you can do to A which take it to the identity matrix. On our last slide here, what we're going to do is to look at a useful theorem connecting invertibility of a matrix and solving matrix equations. What the theorem says is that a square matrix A is invertible if and only if the only solution to the matrix equation A times X is equal to the zero vector is the zero vector. So what I mean by this bold R here is the zero vector, so the vector whose entries are all zeros. That should be the zero vector of the appropriate height so that this equation makes sense. We can prove this theorem now quite easily, because first of all, if we suppose that A is invertible, and if we suppose that this vector V is a solution to this matrix equation, well then you can just multiply both sides by the inverse of A. This is a thing that we've discussed before when we first met invertibility. So when we multiply that on the left by A inverse, what we get is A inverse times A times V is equal to A inverse times the zero vector. Now A inverse times A is the identity, and the identity times V is just V again. So on the left we get V. On the right you've got some matrix multiplied into the 0 vector. But of course if you multiply anything into the 0 vector, you just get the 0 vector again. So what we found is that in the case that A is invertible, the only solution V to the matrix equation AX equals 0 is V equals the 0 vector. And we've done one direction. For the other direction, let's now suppose that A is not invertible. What we have to do is then prove that there is more than one solution to that matrix equation. We've got to find a non-zero solution to the matrix equation AX equals the 0 vector. If A is not invertible, then what we know now is that we can do a sequence of row-ups to A, and we must end up with a row-reduced echelon form which is not the identity. So we know that because we know that if A is invertible, then there is a sequence of row-ups taking A to the identity. So since we're assuming A is not invertible, then when we do a sequence of row-ups putting A into row-reduced echelon form, what we get cannot be the identity matrix. So let's suppose that we can do a sequence of row-ups to A and end up with a row-reduced echelon form matrix, which I'll call R, which is not the identity matrix. Now, since R is a square row-reduced echelon form matrix not equal to the identity, as we've argued before, it must have a column with no leading entry. If there's a column with no leading entry, using our procedure for reading off the solution to a set of matrix equations, which we saw in our last video, what we know is that the variable corresponding to that column with no leading entry can be chosen freely. It's a free parameter. So there's a free parameter in the set of solutions to Rx equals the 0 vector. In particular, if there's a free parameter, then there are infinitely many different solutions because you can choose that free parameter to be anything you like. So the important thing here is just that there is a non-zero solution. Now we know the solutions to Rx equals the 0 vector are the same as the solutions to Ax equals the 0 vector, because R was what you got, was the row-reduced echelon form you got by doing row-ups to A. So since Rx equals the 0 vector had a non-zero solution, Ax equals the 0 vector has a non-zero solution too. We've now shown that if A is not invertible, then the matrix equation Ax equals 0 has a non-zero solution, so we've proved both parts of our theorem.